Hello, this will be a demonstration of Proposition 25 from Book 3 of Euclid's Elements, which requires us to, given a segment of a circle, to describe the complete circle of which it is a segment. We are given then the segment of a circle, A, B, C. Look something like that, A, B, C, like so. And given the segment ABC, our task is to construct the whole circle of which this segment ABC is a segment. On the board, you will see me refer to this circle of which the segment ABC is a segment as simply the circle ABC, since we know it must contain all of the same points. We begin by bisecting the straight line AC at the point D. We do this by proposition 110, of course. Next, at the point D, we construct the straight line DB perpendicular to AC, that's 111, because the point is on the straight line, like so. Some right angles right there. And finally, we simply join the straight line AB, that's postulate 1. Now, given the setup, there are three possibilities. Either this angle ABD is greater than or equal to or less than this angle BAD. So we're dealing with this angle here, ABD. It is either greater than, equal to, or less than this angle BAD. First, we shall deal with the case where the angle ABD is greater than the angle BAD. And if this is the case, then we begin by constructing the angle BAE at the point A such that it is equal to the angle ABD here. That would look something like that. So these two angles here are equal. There's a point E down there. Next, we simply produce the straight line BD to the point E. We do that by postulate 2. We construct the equal angle by proposition 123, and we produce the straight line BD to the point E by postulate 2. And finally, we simply join the straight line EC. Right? Now, given that these two angles here are equal, namely that the angle ABE, which is the angle ABD, is equal to the angle BAE, we know that the sides which subtend them must be equal. That's proposition 1-6. And so the sides subtending the angles ABE and BAE are EA and EB. And so we can say that EA is equal to EB, like so. Now, when looking at the triangles ADE and CDE, we have two sides equal to two sides and an angle equal to an angle. In this case, we have that AD here is equal to DC like that because we bisected the straight line AC at the point D. We did that in the first step. So AD must be equal to DC. And the angle ADE must be equal to the angle CDE because they are all right angles. So we have right angles all the way around like here. And postulate 4 tells us that all right angles are equal. And so we can say that the angle ADE is equal to the angle CDE. And this side right here, ED, is common. And so the triangles ADE and CDE must be equal in all corresponding respects. The important one for us is that AE and CE are equal. Now, we showed previously that AE and BE are equal, so by common notion 1, we can rightly say that CE is also equal to BE, and the three straight lines EA, EB, and EC are equal to one another. Now, what we have going on here is we have three equal straight lines falling upon what is effectively a circle. Right, this is a segment of a circle, so it still has all the properties we could say about the circumference of a circle. And so we have three equal straight lines falling onto a circle, onto the circumference of a circle, and we know that by proposition 3-9 that the point at which they all meet is the center of the circle. And so EA equaling EB equaling EC, and the three straight lines being equal to one another, and falling upon the circumference of the theoretical circle ABC, we know that the point E must be the center of the circle ABC. This is again proposition 3.9. And so if we construct the circle with the center at E and radius of either EA, EB, or EC, we shall construct the circle ABC because it must pass through all 3 points. And so we have done what we set out to do. We set out to construct the whole circle ABC, and we have just found that the circle with the center E and the distance EA is the circle ABC. And so if ABD is greater than the angle BAD, we have accomplished what we set out to do. However, this is not necessarily the case. And so we must move on to the other 2 circumstances, namely where the angle ABD is equal to the angle BAD. And so this state of affairs will look something like that, right? DAB. Right. So we have the angle ABD equal to the angle BAD. Okay, so these angles are equal. Now, being equal, again using proposition 1.6, we know that they must be equal. We know that the sides which subtend them must be equal, that is. And so the sides, or the straight lines AD and BD must be equal. And we know that AD is equal to DC because we bisected the straight line AC at the point D. And so combination 1 tells us that BD will also be equal to DC. And the 3 straight lines AD, BD, and DC are all equal to each other. And now again, using proposition 3.9 in a similar manner, we know that this point D must be the center of the whole circle ABC. And so if we construct the circle with the center D and the distance AD, we will construct the circle ABC, and this is what we set out to do. So we are done with this case. The final case, which we must consider, is if the angle ABD is actually less than the angle BAD. This would look something like that. I'm not even close to happy with that. Excuse me for one moment while I try and construct this segment. That looks something like that. It's fine enough. And so we have A, C, D, like so, and we have B all the way out here. So if we join the straight line BA, like so, then we're dealing with the case where the angle ABD is less than the angle BAD. Like the lights are about to turn off. And if this is the case, what we do is, excuse me for one moment, we construct the angle BAE again at the point A such that it's equal to ABD. This would look something like so. So the point E there. And we see that given this, we see that the straight line BD cuts AC in half and at right angles. So BD bisects AC at right angles. And so we know that the center of the circle ABC must be on this straight line BD. That's the porism of 3.1. And from this point, we have these 2 equal lines. We again know these are equal because the angles here, we know the angles here, EBA and BAE, are equal. And so the sides which subtend them must be equal. So we can say that EA is equal to BE. Just one. Okay. And so on this straight line BD, we know the center must be lying on it. That's the porism of 3.1 again. And we have 2 equal straight lines coming from it onto the circle. And so the only way that all of these facts can be true is if this point E simply is the center of the circle. If it's not E, then one of these conditions will have to be broken. Either that the center is not on the straight line BD or that EA and EB are equal. But we know these conditions can't be broken, and so this point E must be the center of the circle, of the circle ABC. And so if we take the circle with the center E and the distance EA or EB, we shall describe the whole circle ABC, and this being what we set out to do, we are done dealing with this case. And these are the only three possible cases. And so having dealt with all of them, we have accomplished what we set out to do. Given a segment of a circle ABC, we have constructed the whole circle ABC, and therefore we are done with the proposition, therefore QEF. Another little note that Euclid includes after doing all these constructions is the relationship that these segments must have to a semicircle. So if we take the case where we have A, we have B here, we have C there, we do that at point D, and we do that, and we do about that, and we do that, like so. So if this angle ABD is greater than the angle BAD, then the center of the segment will fall outside the segment. And if it falls outside, we know it must be less than a semicircle, because we know that if it were a semicircle, then the center would fall on the straight line containing the segment. But falling outside of the segment, we know that this segment here must be less than a semicircle. Next, given the case where the angle ABD is equal to the angle BAD, except if these two angles here are equal, then we know that this segment here must simply be a semicircle because the center of this segment falls on the straight line containing the segment. And so the segment here, if these angles be equal, must be a semicircle. And finally, it follows that in the case where, that's so much better. In this case here, right? We see that the center of the whole circle ABC falls within the segment, and falling within the segment, we know that the segment ABC must be greater than a semicircle because the center falls within it. These are additional little notes that Euclid puts in. They're not particularly important. Well, they're not important to the construction of the whole circle, but they are, I suppose, true. Not I suppose, they simply are true. So having nothing more to say about this proposition, I will end the video here and move on to 3.26.